there, starting the recording officially. So, we were talking about path models last time, right? So you have to work on this week your last formative assessment that's asking questions about path models. You should be able to answer all of them but the last one based on Tuesday's class, and then we have today's class. Hopefully we'll finish the remaining question. So what are path models for? I think that might actually be one of the questions, but we'll just go over it. When would you need to do this in your life?
You have a variable that you think is like both an independent and a dependent variable.
So as opposed to a multivariate approach as a general philosophy, multivariate via path analysis is especially useful if you're thinking of your variables in a chain of sequence. So this predicts this, that predicts this, that predicts this. Anything that's in the middle that's both a predictor and an outcome, it should be a path model. There are ways to piece it together with a million separate regressions, but that's actually the reason why example 6a was created, was because, I'll show you the picture again. I showed this last time. We're going to get to this at some point, maybe not today, but we'll see. So this path model right here, which had gender moderation to it in addition, the person that I worked with on this, Sarah Gervais, had initially done this as a series of like 30 different regressions, like this to this, and this to this, and this to this, and this to this. And the reviewers were like, oh my God, can you please make this a path model? And so she's like, I don't know how to do that. Do you know how to do that? Yeah, I know how to do that. So we did that, and it was eventually published. So I think that in terms of just being able to follow the logic of connections among variables, having it all at the same time can be more efficient than having a million separate pieces of an analysis, particularly if you're interested in questions about indirect effects, which is whether or not, say, the link between here and here, the extent to which this relationship is different after you control for the intermediate variables, the extent to which that changes across groups or genders in this example. So there's lots of reasons why a simultaneous analysis might be preferable. Another one is general versus generalized. Share screen, please. Yes, thank you, Zoomers. I was intending to do a review, and then I went immediately to start pointing at things. So sorry about that. There we go. Getting the screen share going. And I get the chat window back open and the participants. Okay, now we're back where we were. Okie dokie. So general versus generalized is another reason. If you try to do an approach where you're stacking all of your multivariate outcomes in one column and tricking univariate software into doing it, there is not an easy way to tell it to estimate, say, different submodel intercepts for ordinal variables or different over dispersion parameters for a negative binomial or a beta binomial, like that's all constrained into one. So in order to have each outcome have its own sort of separate prediction with all the pieces that you need to pull that off accurately, path models are the way to go for that. So those are the two that I can think of. And let's see here. What else did I want to say about that? Degrees of freedom. We talked about this last time. A little bit. Should we re-go over it or just review? Do you know the distinction? Re-go over means present it as if you never heard it before. And review means do it more quickly. Any votes? Maybe review? Okay, cool. So degrees of freedom in this context, votes for review from the Zoomers as well. Degrees of freedom is not people. Has nothing to do with the number of people in this context, which is unusual. Because normally when we talk about degrees of freedom, it's with respect to the denominator, meaning that it's the number of people minus the number of fixed effects that you estimated. So denominator degrees of freedom usually conveys the number of fixed effects you could have added but chose not to. And numerator degrees of freedom is the number of slopes. So in this context, degrees of freedom has absolutely nothing to do with the number of people in your analysis. It has everything to do with how many variables you have in your analysis. So degrees of freedom basically means how many parameters could I estimate given how many variables I have, and then how many did I estimate and how many are left over. So total is based on the number of variables. So there's a handy dandy formula here. Number of variables times number of variables plus 1 over 2. That gives you the number of variances and covariances among those variables. And then the extra plus v again refers to the number of means that they carry. So if, for example, you have 4 outcomes, there are 14 possible parameters that I could estimate that are supposed to try to recreate the variables, means, variances, and covariances. And the number left over that I didn't spend is your model degrees of freedom. So this number will show up on your output. Sometimes the number that you estimated shows up on your output as well, depending on which software package you're using. So then there are vocabulary that go with this idea in terms of how many you've spent versus how many are left over. Under-identified, just-identified, over-identified. Vocabulary words. And if you take structural equation modeling with me, you will learn these words in that context, and they will mean the exact same thing. So this is a general concept. So the only situation in which absolute model fit is testable, meaning you can say, yes, the model that I've hypothesized adequately recreates the patterns in my data, is if you are in the over-identified case, meaning you left something on the table. You've overlooked potential pairwise relationships between two variables, and you're letting the model recreate it without them. Otherwise, just identified means you spent everything. So your model is as complex as it can be with respect to trying to recreate all the means, variances, and covariances. Under-identified. What does that mean in English? There's a word I'm thinking of. It starts with a B. No, take bad. Broken. Yes, broken. Under-identified means not solvable. It's like an overdrawn bank account, right? You've spent more than you have. You're trying to estimate more parameters than what is logically possible given the amount of data that you have with respect to the number of variables. This will generally not be the case unless you have something redundant in your model. So an example of something that would be redundant would be like the bottom of this slide right here, where we have two different relationships between these two variables, but there's only one correlation. There's no way to take one relationship and split it into two pieces. It's not identified. Even if it is possible to identify this particular two sets of relationships in the context of a larger model, it's probably still not a good idea. So in path models, it's fairly difficult to wander into unidentified territory unless you do something that's sort of silly. For path models, I recommend shooting for being just identified. I do, because then you can't be wrong. Then you know that all of your results are not subject to being biased because the model doesn't fit. If you're over-identified, there's a chance that you could be wrong, and you have to first show that you're not wrong before you can interpret anything. So the example that I have with the part 2 of the example from, 5? Yes, with the family data, the moms, the dads, and the kids, that model is over-identified because we haven't put in all of the possible relationships between the predictors and the outcomes that could be there. So then we have the chance to test the model fit and to be wrong. That sounds like a review, right? Does that sound familiar? Maybe? All right. Then we were talking about fit last time. So these are the steps of model evaluation within this framework. We can pick up here. Global fit, local fit, those are requirements before, come back here, Mr. Mouse, there we go. Those are requirements before you can interpret anything. If your model doesn't fit, then all the answers that you get from it are probably some shade of wrong. So fit is like a checkpoint that you have to pass before you should do anything else. And there are various ways to indicate that. Local model fit is, even if it fits overall, we want to make sure that there's no big specific problems. But local fit is also a way to improve global fit. So I'll show you an example of what that means here. And then we can talk about what the model actually says about the relationships in your data once we cross these first 2 points. So global fit starts with the idea of the difference between perfect and what you said, where perfect is what's known as the saturated model. In my longitudinal class, we call this the unstructured model. those words mean the same type of idea. It means that you've spent everything. So if you just tell M plus or R Lavon or Stata, hey, just let the variables means be whatever they want, let the variances be whatever they want, let the covariances be whatever they want, put everything in there. That's as good as you can do. And you get a log likelihood for each person, and the sum of those log likelihoods is the log likelihood for the model. So that number you've seen before, right? We've talked about this in terms of doing likelihood ratio tests. It's the same concept. That number, whatever it is, represents the best possible scenario in terms of the height of your data, and your job is to come up with something that is not worse. So the logic of that means that if you have this chi-square test, which shows up on your output, what this is a comparison of your model, which is usually called HO, against the perfect saturated model. And because you want it to be not worse, what we're shooting for with respect to the p-value that goes with the chi-square is non-significance. So this is logically backwards from what you're used to. Non-significance is good, because what it means is that there's no difference between perfect and what you said. Significance is bad. There are rules that you may see in papers like, well, I have significance, but my chi-square divided by my model degrees of freedom, meaning things left over, is greater than 2 or greater than 3, so it's fine. No, don't use those rules. However, just like some of you have probably seen in your individual analyses, if you have a very large data set, you are never, ever going to have a non-significant chi-square. It's never going to happen, because you are overpowered to detect small differences. So any tiny deviation between perfect and your model will be picked up by this if you have a very large sample size. Based on that, and based on the idea that perfect is an unreasonable goal, then there are other ways of indicating model fit that are referred to as absolute fit indices, which are relative to perfect, and then what's known as comparative or incremental, which are relative to a worst case scenario instead. So here are some of those. It is alphabet soup, basically here. There's a bunch of acronyms. So there's SRMR is one index that you'll get. This is one that's relative to perfect, standardized root mean square residual. I have the formula here, but I can explain it more simply. This is the average offness in a correlation metric between what your data say and what the model says, what the data want and what the model says. How far off is each pair of correlations on average? 0.08 or less is conventionally indicating good fit. So another tip, when you see words like residual or error in the name of these things, that means you want them to be small, because they are relative to perfect as the standard. Here's another one, RMSEA, root mean square error of approximation. Also want this to be small. This is how far off you are from perfect per degree of freedom left. So it has a penalty function where if you try to add things to your model to make it fit better, but they don't really help, this will actually get worse because you're adding garbage, basically. It wants you to have a tight, parsimonious model, and it will increase to the extent that you've spent extra parameters that didn't really help it fit better. This one has a lot of words that go with it, and different authors will use different cut points. So less than 0.05 or 6 is good, 0.05 to 8 is adequate. There's a lot of euphemisms. I don't buy into the labels, just tell your audience what it is. RMSEA is 0.07, call it what you want. You also get a confidence interval around it, and that confidence interval will be wider and smaller samples, as it should be, indicating that you have less assurance in what that number actually should be. And it also provides a test of close fit, which is whether or not it's less than 0.05. So this is a different standard than perfect. It's like good enough. It's known as close fit, and that is a term that everyone has agreed on. Then there are the other family. How much worse than perfect were the first two. The other ones are how much better than terrible. Seriously. So this is relative to what is known as a null model as the baseline for comparison, where it says, okay, let the means be what they want, let the variances be what they want in the data, but say no covariance whatsoever. The null model says you have nothing worth modeling, nothing is related. Fight me. And so then you put your model in here, and it's how much better did you do than saying there's nothing to model here. So because it's phrased as relative to the worst alternative, then these are bigger is better in terms of direction. So the CFI and the TLI, you want better than 0.95 ideally. CFI is capped at 1 because of the way it's computed, whereas this one can go above 1 or it can actually go negative. The TLI is also known as the NNFI in other software packages. So yeah, you'll get like a whole list of these things every time you run a model. And of course, they don't tell you what's good or bad. But as a mnemonic, if it has the word F in it for fit, it means bigger is better. If it has the term residual or error, that means smaller is better. So we look through this list here, and we see if our model meets conventional standards. If not, the reason for it, most likely, is some pairwise relationship that has not been adequately recreated without having a direct path between those two variables. So then we have to figure out why that might be. So these rules, by the way, it used to be that once upon a time, everyone agreed on what these standards were in terms of what good is because of one study. So there was a simulation study published over 20 years ago that has been cited over 100,000 times, where they looked via simulation. So this means that what they did is make up data where they know what the right answer is. And then they deliberately mess up the model in prescribed ways to see how well these different indices can figure out whether it's wrong or not. And based on that process, these authors recommended those cutoffs, like CFI greater than 0.95 or RMSEA greater than or less than 0.08, etc. But since then, within the last, I'd say 10 years or so, folks have started to focus on the fact that this one study only covered certain situations in terms of the complexity of the model, the sample size with respect to people, the number of variables that's included, the number of latent factors in the context of structural equation modeling. And then they've started to see exceptions to these rules appear when you actually try to dive deeper. So I have a lot more content about this in the SEM class where it's more relevant. I point you towards that class, but just know that there's not necessarily these days the same dogmatic, it has to be 0.05 or less or I won't publish your paper, that it used to be. Because those standards can't necessarily fit every problem. So a caveat with that. Now, if your model doesn't fit, what do you do next? Because in most cases, this is where you're going to be at. It's your job to figure out why. So then we get into the idea of identifying what is either known as local misfit or localized strain. And all of the ways to do this are predicated on one basic idea. You've got your covariance matrix of the answer key, what the data say they want the variances and covariances to be and what they want the means to be. You got what your model says they should be. And then you look literally at the discrepancy in every single spot. And there are indices that tell you how large those discrepancies are in various metrics. So the residual output is how you get this in M+. It's also the residual function within R-Levon and SStat residual in Stata, so they've all agreed on the same terminology. And they will give them to you either as covariances, which are difficult to interpret because those are scale specific, as correlations, which tend to be easier to interpret because we know how big a correlation should be, or this kind of way of z-scoring it to divide the residual discrepancy by the standard error of the parameter. So these normalized residuals are trying to sort of highlight which spots are relatively more problematic based on how precisely that model parameter would have been estimated in the data. So if you see a positive number, that means that the outcomes are more related than you predicted, meaning you've missed something. That's almost always going to be the case in path modeling. So if you leave out a direct relationship because you think the rest of your model should cover it, you can be wrong, and then the outcomes actually have a larger relationship than what your model says. Negative means they want to be less related. That is more likely to happen in the context of factor analysis than path analysis, but it's also possible here. So these patterns, you will literally get a matrix of output, and I'll show you an example of that, that tells you sort of where the problems are. But then it's up to you how to fix them. So it tells you where the problems are, but not necessarily what the right strategy is to repair your model. So people have figured out a way to do this. And you can also ask for another piece of output known as modification indices. I call them cheat codes. So any people who like to play video games in here? Or people with children who do? Or people who used to play video games but now you don't anymore? That's most people, right? Between those three categories. So I remember when my younger brother, he's 4 years younger than me, got his first Nintendo. He had saved up all of his birthday and Christmas money, and I have never seen him to this day more happy than in that moment when he was like 9-year-old boy carrying home the Nintendo from Target. And he bought like one game, right? Because it was like in $1989 or something, was still like $60 a game. And that was all he could afford. And you also used to be able to buy these magazines that would like show you how to cheat the game, right? Like, here's where the hidden turtle is. If you bop this block that doesn't look like anything, you get an extra life or whatever. So I think of these modification indices as like that magazine. It's like, hey kid, come here. You want your model to fit better? Put this path in here. It'll fit. But that path doesn't make any sense. I don't care. It'll fit. So the modification indices are not theoretically meaningful. They are totally reacting to the data that you have, and they will fix it. Whether it's fixed in a good, reasonably defendable way, or whether it's just stick it in here, it's fine. They don't care. So you can look at these, but you have to look at these from a perspective of, does this make any sense? Because it will list a whole bunch of stuff that makes zero sense, particularly when you get into latent factor land. Within path analysis, if you're missing a relationship between two variables that needs to be there, there's really only two choices. You can put in a slope of one variable predicting the other, and it's up to you which way that goes, or you can put in a covariance that says, just let them be related. I'm not going to say which comes first or anything like that. Those are your two choices. So every time you look through this list of what you could do to make your model better, if you change it, put the new thing in, the list shuffles. So it's going to react differently at each step if you go through this in an iterative process. So it's up to you to take this information and use it in a meaningful way. It doesn't know or care like what's meaningful in the context of what the variables mean. That's on the side of the analyst. And that's why I'm pretty sure that like ChatGPT is never going to replace us with this type of thing, because it can make the model fit, but whether it's garbage is a human consideration. So we go through this process, check the fit, see if we can make it better in a reasonable way. Once we're done and it fits well, then we can actually look at what we have and try to understand the results. So I want to formative assessment last question here. Highlight a very, very salient point of misunderstanding that I see and I've answered dozens of questions about over the year. Fit and effect size are two different things. So if we talk about in regular regression and we want to talk about effect size of our model, how do we do that? Like if you're back in regression land, right? Not this class, but wherever you came from before it, and you want to talk about effect size? The magnitude, how would I operationalize effect size?
Like how practical it is, like in the real world.
Like literally what numbers would you give someone if they said, I need an effect size or I won't publish your paper?
Like 0.08 or
That's power.
Oh, sorry.
What kinds of measures of effect size have you seen before?
Just G.
Sure, a G and also the D family. There's like etas and eta squares. There's R square, right? In regular regression, you can talk about the proportion of variance that is explained in your variable as an effect size. And that goes along with statistical significance. So you can have a parameter that's significant but not very meaningful in terms of the effect size. Or you can have a very large effect that's not significant because you don't have enough people to make it significant. So some folks might say that the model fits better after you put predictors in it. That's not exactly true. And that distinction is relevant here. So let's say that I have this path model, And I've had people email me almost like literally this question. This is not made up. Let's say that I have a path that's 0.01. These are standardized paths, so these are in a correlation matrix, 0.05, 0.03, and 0.02. And this model fits very, very well. All the indices agree that this is a great model. Trouble is, none of these paths are significant. They're all tiny. So how can that be that I have a great fitting model, but yet none of my slopes are significant? How can that be? They're not, but then how can my model fit so well? Is it explaining the not good at fitting? Yes, I think the words are not quite in the right order, but I know where you're going and you're right. Yes, you want to try? That could be the case if they're super highly correlated, and that would show up then as a large like R square, but then individually these are not uniquely significant. But let's say that the R square is crappy too. So what does fit mean in this context? The hand gestures I've been doing all day. Right, we have the model says what the means, variances, and covariance are supposed to be. The data say what they're supposed to be, and it's how far off they are. That's fit. So this model can fit very well because it perfectly recreates the non-relationships that there are among your variables. It adequately gave you the zeros back that actually were there in your correlation matrix. That's what this means.
So it's just so hyper-customized to your data that it has no other use beyond that?
I wouldn't say that it's necessarily hyper-customized, but what I would say is that if you had looked at a correlation matrix before you did your path analysis and you see a whole bunch of zeros or tiny numbers, like game over. Like the path model is going to adequately recreate the non-relationships among your variables. So from the perspective of how well can I predict y1 and y2, the fact that my model fits is a precursor to answering that question, but it does not mean that these are predicted well. Quality of prediction and effect size are logically separate from how well the extent of the relationships is captured by your model. So it can fit and have garbage results in terms of the strength of the relationships, or it can fit and have really strong relationships because that's just what's in the data. And we've never worried about fit up to this point because we did univariate analyses where each variable had whatever leftover variance and whatever mean or intercept or threshold submodel parameters were needed, and we didn't ever try to do anything else. So distribution fit is related to this, but it's a different issue because this is just assuming we've got the distribution right and we're trying to summarize the multivariate patterns in the data. So yes, the Zoomers are saying in the data set, there is a non-relationship between the variables. Yes. So good fit is a precursor to interpreting your slopes, but it does not guarantee you of anything worth interpreting. The same thing can happen in factor analysis, by the way, too. So you can have a latent factor that does not significantly predict any of your outcomes if the outcomes weren't correlated in the first place. So step one would always be to stare at a correlation matrix and see if you have something worth modeling. Because the job of the model is to recreate that correlation matrix. At the end of the day, that is what it's doing. All right. Questions or comments so far? I think we get to do an example next. How about that? Numbers usually make things better. Maybe not equations, but maybe numbers. At least for me. I always have a hard time reading textbooks that are written in an abstract way, like with just letters and like symbols and stuff. And I'm like, can I have a noun or something in here to keep something in my head? Let me give you some nouns. So this is part 2 of example B that I'm switching to. We did the first half of it in Stata mixed, SAS mixed, what's the other one? What did I do with this? GLS, that's what I did with this. Because this is a multivariate analysis in which each variable is either a predictor or an outcome. So I'm using this as a way to introduce path analysis software and output. So the first step that I'm going to do is re-estimate the last model that we ended on and show you what it would look like as a path model instead. So let me remind you then where we left off. So I had, to do these previous analyses in part 1, I'm on page 9 here, I had stacked the data from wide form to long form so that I had 3 outcomes for each family as my unit of analysis here in one column. I had attitudes for the mom, attitudes for the dad, and attitudes for their adult child with respect to gender marital roles, where higher scores mean more conservative attitudes. I had controlled for who's who. So this parameterization corresponds to what I call outcome-specific intercepts. That way, the dad, kid, and mom variables here, these are dummy codes that work like switches to activate each parameter with respect to each row, so that the terms that are supposed to predict dad are turned on when it's 1 and off when it's anything else. And we had controlled for each person's education on their own attitudes. We had also controlled for whether the adult child was a boy or a girl, or a man or a woman, as it were, on the score for that adult child's outcome. And then I had added effects of dad's education in predicting the child's outcomes and in predicting the mom's outcomes. And we found that there was no effect of your own education for kids and moms. There was an effect of your own education for dads, which was negative. In this context, that means more educated dads had less conservative attitudes. And there was no effect of dad's education on the attitudes for kids and moms. And that was the end of the story. So then I have words to describe it, check the distribution fit, said it was reasonable enough. So now I'm going to turn that same analysis into a path model, not because I need to, but because I want to demonstrate the equivalence of these 2 approaches within this context. And because I'm trying to make everybody happy, I have it in multiple software packages as usual. So now I'm on page 11. So first thing I got to do is create a data set to be used in M+. So M+ is 1985 when it comes to dealing with data and input and output. They've put all of their energy into the what's under the hood estimation part. So to use M+ software, you have to provide it with a data set in text format, meaning tab delimited or comma delimited data, and the top row that normally would have data names for the variables has to be gone. It also doesn't require, but I've had much better luck when I do this, requires filling in missing value codes rather than blanks. Particularly, I've had problems reading in data that have like a lot of decimal values, because then the dots for the, like it gets confused with that. So this may be superstitious behavior, but I still recommend it. So I am taking the data set that I had created for this example that was in the original wide format. So that's the version where it's 1 row per family and all the variables are in separate columns. I am replacing all of the blanks with actual minus 999 values. The reason I picked that number is because it's unlikely to occur naturally within any of my variables. And then I used, this is Stata code to export the resulting file into something that M+ could use. Here's our code to do the same thing. So I used the isNA function to replace the missing values with minus 999, and then I used write table to export it to this file. So here's the same model again, just repeated the equation so that it was clear what the following code was to refer to. So first, with Stata, I'm using a new function, SEM, stands for structural equation modeling, which is able to do relationships among latent variables or observed variables, as you wish. Note up above here the distinction between 3 slashes and 2 slashes, all in green. Took me a while to get this right. So in older versions of Stata, I'm told that this has gone away in recent versions, but I have my code written this way so that it remains backwards compatible. Do you see all the 3 dashes here, the 3 lines all the way down? That is what's known as a line continuer, because according to Stata, all of this is one line of code in terms of its instructions. So to get it to keep reading as you return lines, you have to type this. Now note the last one here only has 2 slashes and not 3. That's just a comment. So it's not a line continuer. This is now a separate set of pieces of code here. So fortunately, after the line continuers, you can add comments as well. And so I have written out what each chunk of this code is trying to do. So in the original data set in wide form, I've got 3 outcomes: kid marital, mom marital, dad marital, and I am predicting them. See the less than sign with a dash after it? What does that look like when you put it together? It's an arrow. Yeah, it's like an old-fashioned arrow. So what I'm doing here is saying I want a constant to predict these things. That is a roundabout way of saying I'd like all my intercepts to be estimated, please. Each outcome gets a separate intercept. That is the analog to these 3 terms right here. Then I have outcome, predicted by, and then predictors. I wrote it this way to be consistent with what it looks like in the other packages, but Stata lets you make your arrows go either way. You can choose which way they go. So then these are the regressions. So I have the first 2 right here, kid gender and, wait, here it is. This one and that one. Kid gender and kid education predicting the kids' attitudes. Mom's education predicting mom's attitudes, and then dad's attitudes predicts all 3. So what this is doing is building 3 simultaneous regression models where I have whichever predictors of each that I feel like having.
And that's just driven by your theory.
It's driven
Right,
by my theory and my questions. Yep.
Okay.
Yep, in this case, I could have loaded it up with every combination of every predictor and every outcome, but previous analyses in this example had shown that I don't need to control for the gender of the adult child in predicting the mom and the dad, and I hadn't yet considered whether the kids' education should predict their parents' outcomes. That seems less, like, that seems a little weird. Like, things roll downstream, not upstream. And I haven't yet considered mom's education in predicting the other people in the family, but I have considered dad's. So I am missing some pieces, perhaps deliberately, so I can show you how to troubleshoot misfit. But yes, it's completely up to you, the order these things go in, the way that you describe the relationships, which way the slopes go, and whether or not you want to have slopes or covariances as well. I will also say that in every example, not just in Stata, but in all the other packages, I write out everything in my code, but not everything has to be written out to get this model to go. My approach is to be as transparent as possible about what is going into the analysis and to not require people who are looking at these examples to remember what the defaults are, because the defaults change and they differ by package. So I write out everything. I'm pretty sure that, for instance, each variable gets an intercept by default. Each variable probably gets a residual variance by default, but I'm writing those things in here. So then this line right here that starts with var, with the E in front, that says, hey, give me a leftover variance for each of these things, please. And then I would like all possible pairwise covariances among my outcomes. So these would be depicted as curved arrows amongst the boxes for each of the attitudes across the 3 people. I'd like it to do full information maximum likelihood, so try to use whatever data we have as opposed to kicking out cases with incomplete data. And then the last piece here, these are lincoms that do linear combinations just like we have done all semester. The only difference is that you have to understand how Stata is labeling the slopes in order to have it do math on them. So that's what this piece right here does. And there's a piece of output that tells you for each parameter what it's known as internally. So for instance, I had to refer to this piece of output to understand that this is the effect of dad's education on mom's marital, and this is the effect of dad's education on kid's marital, and by taking the difference between them, I'm asking, does dad's education have a greater effect on the kid's outcome than the mom's outcome? And the same with kid versus dad and mom versus dad for all the combinations here. Then I'd like to get the standardized solution. I'd like all the goodness of fit. I would like to know what the log likelihood is for the perfect model, because that's one of the questions I will ask you in your homework. I would like the R-square for each variable, and SStat residuals is the troubleshooting index. I would like to know how far off each predicted element is from my model relative to what it is in the data. And then I would like the cheat codes, which I used to call them voodoo, but I didn't want to offend anybody, so I changed it, but I forgot to change it here. There. Cheat codes to improve model fit. And the 3.84 is because that corresponds to a chi-square critical value for 1 degree of freedom. So basically I'm saying, show me all your cheat codes that will improve my model significantly. All right, questions so far? So Stata has a whole bunch of output. It starts off with different pieces in different orders relative to the other packages, but once you get used to seeing it, it's fairly straightforward. So we have the unstandardized solution, and then we have whatever's being predicted out here, and then all the different predictors. And this out here is me being nice and trying to label them to what the equation said they would be, to tie it back to the model that we fit in the univariate package. So this is not Stata output, this is me being nice. So like this right here would be if I did a regression predicting kids' attitudes, and that's it. There's my solution. The constant is the fixed intercept for the variable. This is the slope of dad's education predicting the kid outcome, kid's education, and then the gender of the kid. So we get coefficient standard error z, because we have no denominator degrees of freedom in these models, and then the p-value, and then the confidence interval around the slope. Then we get all the relationships predicting the mom outcome, and then the dad outcome. Next up is the variances of the residuals for each outcome, along with the 3 covariances among them. These things would build my R matrix. Here's one piece of information about our model fit. The rest of it is available later on. But if I look at this right here, it looks like our model fits, but is close to maybe not fitting. So the chi-square there is 0.09, which is technically non-significant, but it's still too close for comfort. Here's the linear combinations that I asked for to contrast the slopes. And then here's COEF legend, the output that tells you what all these things are called so that you could do math on them as needed. Then we get into the standardized solution, which is the exact same information, but in a metric in which each outcome has a variance of 1 and a mean of 0. So these are all in correlation form, more or less. Then we get into fit statistics. So before I can interpret any of the slopes, I want to stop by and make sure that the model actually fits. So we have likelihood ratio chi2 ms6. What that means is that this is the likelihood ratio test, the difference in -2 log likelihood between the perfect saturated model and my model. The 6 in parentheses is the degrees of freedom for the model, the number of things I could have added but didn't. The p-value then is 0.09, which is actually good news because it's non-significant, meaning we're not worse than perfect. But that's overall. I would still want to make sure that there's no individual specific problems with respect to pairs of variables. I don't know why it gives you this. This is useless information. All the packages give you this. Baseline versus saturated. That one means, is the worst worse than the best? Has nothing to do with what your model is. Yeah, that face, exactly. Like, what? No, Why do I care about this? The only situation in which you might care would be like, do I have anything worth modeling? Because the worst model says you have nothing worth modeling. And if it doesn't fit worse than the best model, that means you have nothing worth modeling. So we can step on by that. RMSEA is the next box. The answer is 0.077, so not terrible. The p-value of close fit is less than 0.05. The p-value is non-significant, meaning close fit holds, so yay us. However, the CFI and TLI are not quite high enough. So we get 0.87 for CFI and 0.67. So these indicate that we have a little bit of work to do. And you might be asking yourself, how is it that these ones think it's fine and these ones thinks we have a little bit of work to do? And the answer is yes. They will disagree because they're based on different standards. Baseline comparison is how much better am I than the worst possible, whereas these ones are how much worse am I than perfect. Then we get into R-squares. So these are the R-squares for each variable. So we've captured 5% of the kid variance, not very much of the mom variance, and 7% of the dad variance. Then we get into the residuals section. So this is our local fit. The residuals tell us, data say this, models say this, what is the difference between the two? So the first thing that we have is raw residuals for the means. And these are all 0, as they should be. Because every variable in this analysis either has an intercept if it's an outcome, or doesn't need one because it's only a predictor and it's not a model parameter. So the fact that these are all zeros means there's 0 discrepancy. Fit is perfect with respect to the means. Then we get down into the covariance matrix. The diagonal of the covariance matrix is the variance of each variable, and these are mostly perfect, very close to right, but I've highlighted the biggest sources of discrepancy, which are right here. So we have kid marital and mom ed, mom marital and mom ed, and dad marital and mom ed as the big sources here. So what that is telling me is that those relationships of mother's education to the 3 outcomes are not adequately recreated by this model. In particular, there is a negative relationship between dad marital and mom ed that's not adequately recreated. So the negative residual means that it's a negative relationship. That's because this one's not in there. Likewise, mom ed does not predict kid marital, so that one's missing. But this one actually is in there. The 0.07, mom marital does predict her own scores. So there's no way that I could fix this. This is a consequence of other things being missing and skewing the whole picture. So we're not getting the right answer for what the mom marital to mom ed to mom marital slope is because of these other missing pieces of information. So this is just reiterating that we don't want to look at the results and interpret them until the whole thing fits well. Modification indices, cheat codes. There we go. It's like, hey, if you put in a slope for mom ed predicting dad marital, then MI means your chi-square is going to improve by 9. That's modification index. So that's how much of an improvement in fit you could anticipate by adding this parameter. And indeed, that's the one that up here, that's the biggest source of the discrepancy. So we can do it. All right, R code. Lavon. The fact that all of this is green is not an accident. In Lavon, the way that it works is that you create an object, which I've labeled syntax 3 since this is model 3, and it starts with a quote, and then the whole thing, it has an end quote. So you save all of this code that tells it what kind of path model to build as one object, and then you feed that object into the lavaan function as the type of model you want to fit. So this makes it difficult, I think, at least in my version of RStudio, these are all the same color. Lines that begin with this hashtag are comments. Lines that do not are actual pieces of code that R is going to use. And Vladimir, do you know, is there a way to fix that? Because I know your colors are different than mine. No, you don't know? Or you can't fix it?
No.
You've never tried?
No.
Okay, yeah, this is all learned helplessness. Like, okay, R, fine, it'll just all be green. I don't know what to do otherwise. So what I have done here is in the line above, the comment says what the line immediately below it is doing. That way, hopefully, this becomes a little more transparent. So first thing I'm asking for is residual variances for each of my outcomes. The way to do that is to list the name of the variable, and this is case sensitive, by the way, the same variable on the other end, and then squiggle, squiggle in the middle, which most people would call a tilde, I think. That sound right? It's the thing that's above the tab key on the left. I have semicolons separating out different commands so that I can condense the code onto fewer lines. If you want a covariance between different variables, then that's the name of the variable on one side, the name of the other variable on the other, and then squiggle, squiggle in the middle. And you can add plus signs that don't do plussing. They don't, as my child would say, they don't do plussing. This just means kid marital is correlated with mom marital and kid marital is correlated with dad marital. So it's just a shortening of the expression. And then mom marital is correlated with dad marital. For the intercepts, which we want, it's the variable one squiggle and then the number 1 for a column of ones, like the constant was in Stata. The same single squiggle is used for the regressions. So I have kid marital, for instance, being predicted by kid boy and kid ed, where the order matters. It's the outcome and then squiggle and then the predictors. And if you put words in parentheses in front of it, that is a label so that you can then do math. So for instance, if I wanted to contrast the effect of dad's education on the mom versus the kid, then I can make a new term that is K versus mom, dad, ed, out of, and this is colon equals, the label for dad's slope of dad education predicting kid marital, and then this one is the label for dad slope predicting, that one's kid, this one is for mom. So I'm using few characters as possible to keep the code consistent with M+, but it gets to be a headache after a while, but then I've labeled what they are out here. So everything is in here that is being estimated in the model. Some of this happens by default, but again, I'm trying to be transparent in what happens. Then we feed it into the lavaan call. It wants to know what your data set is called, the object that contains all the syntax, what kind of estimator that you would like. So I am actually asking for MLR, which is robust maximum likelihood to make a point. And then it does something that I'm not entirely sure about, but it's meant to mimic what other programs have, and the one that I'm mimicking is M+, because that's the one that I use most of the time. Then we have extra things, part of summary. I would like it to tell me the fit indices. I would like it to tell me the R squares. I would like it to give me the standardized solution, and I would like some confidence intervals too. And then based on that analysis, I'm asking for some more stuff to be printed. I'd like to get the modification indices, so the cheat codes to fix my model, and I would like the residual covariance matrix so I can see what the cheat codes are operating on. So I don't have the lavaan output for this model. I'm going to have it for the next one instead. But I do have M+ code here as well. So here is what M+ looks like. M+ is a standalone program where there are two kinds of files that you have, .inp and .out, input and output. Both of these are text files. So you can edit and read M+ input and output in any text editor. It doesn't have to be inside M+. Unlike other programs where you can just highlight a chunk of code and just run that chunk, that does not happen in M+. It reads the whole file for better or worse. So what ends up happening if you want to have multiple models in the same analysis, you either have to make a separate input file for each or comment out the one you don't want to run currently. Separate files for each can get into a headache quite readily because then you have a million files, and if you don't name them carefully, you don't realize how they differ from each other. There is an R package called M+ Automation that I am told makes this less of a headache. I have not played with it, but people say nice things about it. The colors in M+ syntax are similar to what they are in other programs. Green is comments, except the beginning of a comment is an exclamation point. Blue is for M+ dedicated commands, and black is everything else. M+ is not case sensitive, and M+ is not space sensitive. It's also not line sensitive. You can keep like dropping lines forever and ever, but it does use a semicolon as a command terminator for each idea. There's a few other tweaks though that you have to remember. One of this is right here. M+ will only read 90 characters across. So if you keep typing, it ignores what you say. It will throw an error message when that happens. But I've seen models not work because the part that was important was at the end of the 90 lines and it just skipped over that. The other thing is that every variable name has to be 8 characters or less, 8 characters or fewer. So that means you may have to get creative in naming things. Since the data coming in are a text file without names though, it doesn't know what they used to be called. So you can rename these things as you wish. This is the package that I use in the structural equation modeling class predominantly. This is the package that I use in the advanced longitudinal class. So I would recommend learning how to do it if you can. You don't have to, but I would recommend it. By the way, your last homework is now available, which is a path model. And you can use Stata, R, Lavaan, or M+ to complete it. They will converge onto the same answers. Unlike previous homeworks, there's one model, just one. So once you get the log likelihood, you're home free. But it may take a while to get to that point. So it's fake data that are based on real data on a publication where the person had done 2 separate path models for basically no good reason. And so the instructions are telling you how to put the 2 together. So if you are looking for ways to procrastinate on final projects or grading or any other thing you don't want to do, might I recommend starting homework 6. Then you can be productive and not feel bad because you're doing your stats homework. So along with that, I have a starter file for M+, and for the other 2 programs that will allow you to read in the data, make sure the missing values are handled and that kind of thing. If you're going to use M+, though, you will have to make your own CSV file. So I would recommend opening the data set in Excel, removing the first line, and then saving it as CSV, which is what I do. So in M+, given that the names are not in the data set, that's the very first thing it wants to know after you tell it where your data are. So file equals is the name of the file. So this is the name of the data set that I have. Format and type, just tell it what kind of data it is. These are the defaults to have individual row data as opposed to matrix input. For names, these are the names of every variable in your data set in order. I cannot stress that enough, in order. A lot of times I have troubleshoot what people thought were terrible models only to find that it wasn't reading their data correctly. Like they had transposed the names of 2 columns or something, and that was the whole situation.
So it's like the order that it's
In the CSV file. So like I would literally like try to save the row of names and then just like paste it in here as the names. It will work. It will look like funky in terms of the spacing, but it will work. And then if it goes past 90 characters, just make sure you hit return and send it to a new line if you have a lot of data. So because you end up having to write out all the names, in practice when I use M+, I tend to cut my data set down to just the essential things that I need and not have anything else in there because I don't want to type 500 names at the top of this list. Then it wants to know, okay, of the columns, which ones are you going to use today? If you forget this, it will try to put every single variable into your analysis and it will not go well. So then you tell it which ones you're using. So I'm using kid gender, the 3 educations, and the 3 outcomes. Tell it what kind of missing data code you have so that it will read your data correctly. Then analysis, what type you have, which most of the time type equals general will be fine for what you need. estimator, MLR or ML for these models. We're going to start with ML so that it's the same as the other SAS and Stata examples in the univariate case. Confidence intervals, standardized solution. It's like, it would be better not to have a semicolon after this. I know, but M plus wants one. So, sorry word, M plus is going to overrule you there. Residual is the output that tells you how far off you are for troubleshooting misfit. And then mod indices again with the 3.84. This is the cutoff for significance for any individual parameter given a chi-square distribution. Then we get to model, where you actually tell it what you want. So in M plus language, there are a few things that you need to know. When you list the name of a variable all by itself, you are referring to its variance or its residual variance. It knows which it is based on the rest of the model. Stars are used to indicate free parameters to be estimated. They are somewhat redundant in that you don't need to type them in many cases, but I tend to stick them in there just so that it's obvious what's being estimated and what's not being estimated. So listing the three variables by themselves, followed by the semicolon, means that I am asking for the residual variances. Then note this compact sentence right here with a with in the middle. With is how you let things covary. So if you just want things correlated or covaried, that's with. And stacking the same list of things on both sides of the withs mean give me all possible combinations. So I get all three possible covariances among my three variables in one line of code. Then things in brackets. Right here, those are either intercepts or means, depending on your model, where an intercept means it's predicted and a mean means it's not predicted. It knows which is which based on what else is happening. Then we get to the regressions. So you can stack up your code to have multiple outcomes and multiple predictors on either side of this on. Think of the on as the equal sign. So it's like y equals predictors. It has to go in that order. So kid marital is being predicted by kid education and kid gender. Mom marital is only being predicted by mom ed. And then dad ed is predicting all three of these at the same time. And I've added 3 labels for what those slopes are going to be called so I can do math on them. Then model constraint is the analog to LinCom in Stata, GLHT in R, or estimate statements in SAS, in that you can ask it to do math, make linear combinations of your parameters. So the way it works is that you have to first come up with the name of the new thing you're trying to create, and then you tell it how to make it. So these are the same labels that I used in the other packages for transparency. But this first one, for instance, wants the difference between the slope of dad's education in predicting the mom's outcome versus the kid's outcome. So this tests the difference across those slopes. So anything that you make in here, you'll get a significance test for as part of your output under the heading New Parameters. All right. Any questions on syntax? Cool. Then we have, I think, just enough time to look at this output. So M plus shows you the fit of the model first, which I actually prefer because that's like do not pass go, do not keep going if it doesn't fit. First thing it tells you, how many parameters are in your model? 15. That means how many things are you estimating? Log likelihood. HO is U. H1 is perfect. Information criteria, same thing that we've used throughout the semester to supplement log likelihood ratio tests and log likelihood comparisons. We can ignore those, but smaller is better. Here's my chi-square test of model fit. So this is the thing that compares best model to my model, and we want it to be not worse. So the chi-square test statistic is 6.929. 6 is degrees of freedom, how many things we could have added that we didn't. And the p-value is 0.09, meaning it is non-significant. So technically this fits well, but we want to make sure that we don't have any local fit problems. This is an overall index of fit instead. RMSEA, do we want that one to be as small as possible? Test of close fit is non-significant, which is good. It means we have a close fit. CFI and TLI are not good enough, which is the same output that we saw for the other ones. Chi-square test of the baseline model, this is worst versus best, no one cares. And then SRMR is another relative to perfect index, so we want it to be as small as possible. So this one's okay. Then we get into the model results that are unstandardized, where it lists the thing being predicted first and then the predictors of it underneath. So the first column is the estimate standard error. Estimate over standard error, what do we call that? Otherwise known as a letter. There's only 26 to choose from. Z, yeah, that's our Z. It would be a T if we had degrees of freedom for the denominator, but we don't do that. And then two-tailed p-value. So then I annotated this to show how this corresponds to each of the equations or spots in the R matrix. But these are your regression slopes for each outcome, your intercepts for the 3 outcomes to be predicted, residual variances, and then these are the linear combinations we asked for. Standardized solution gives us the same information on a different scale, on a correlation metric instead, and it also gives us the R-square for each of the variables. Then we get to the residual output that helps us troubleshoot misfit. So residuals for covariances, this is literally how far off each covariance is from the data, perfect model versus what we said, our model. And it's the same pattern of the 3 being related to mom's education. Here's the model constraint, after shutting off model constraint rather, here's the modification indices that tell us our chi-square would improve by 9 if we put a slope from mom's marital, or excuse me, what I want, that one? Yeah, this one, this 9. Mom's education to dad's marital. This one doesn't make any sense. This is an example of it just saying, okay, here you go. It wants mom's marital attitudes to have a slope predicting dad's marital attitudes. That's already in the model as a covariance between the two. So if we actually did what it wants us to do for this first suggestion, we would break our model. It would be not identified. So we only want to pay attention to suggestions that make sense and aren't duplicating what we already have. So it looks like all 3 programs have converged onto the same suggestion. Mom's education needs to predict dad's attitudes as well as her own. So that's what we'll do next time. But that will be next week because today is Thursday, right? Okay, got it. So, to be continued. All right, 312. So questions before we call it a week. So this isn't really that different than what you already know how to do. It's just doing it all at the same time in a little bit of a different language. So, but once you get used to it, it's not bad at all, just complex. All right, then you have a formative assessment due Monday. I will be in touch regarding your homework 5s. I'll be having fun all weekend grading. Hopefully get most of that done over the weekends. We'll see. And next week we'll finish up path models, and that'll be it. So thanks for being here. See everybody on the other side. Let me know if you need anything.